After talking about electric current and electric potential difference, we'll now look at how to mathematically or algebraically solve for these different types of electrical quantities. And to do so, we will use Kirchhoffs laws as one way of understanding. So Kirchhoff was a physicist who studied electricity, and through a number of experiments he did using simple series and simple parallel circuits, he was able to determine some properties of potential difference and of electric current. So first, let's understand how a simple series and a parallel circuit operates. The first question here, when charges have several loads to pass through, what governs the amount of electric potential energy they lose at each load? So when we have a series circuit, how do we know how much energy do we drop, or what's the voltage drop across each of these loads? That was the first question that Kirchhoff looked to solve. The second question, when charges may follow several different paths, as in a parallel circuit, what is it that determines the number of charges that each path takes? So let's say we have, in a simple case, 4 or 5 or 6 electrons, and they start to come across these paths here. How do we know which paths these electrons take? And do 3 of them take this path, whereas 1 takes this one and 2 takes this one? Or do 2 go down each one? So these are the kind of questions we have to ask, or that Kirchhoff really asked, and he looked for a solution, and he did some simple experiments using these circuits. These are governed by what we now call Kirchhoff's voltage law and Kirchhoff's current law. The short form of these are KVL and KCL. I should mention here, Gustav Kirchhoff was a German physicist, and this was in 1845 that he answered these questions through his use of experiments with series and parallel circuits. So please copy what you see down in green here and label this as Kirchhoff's voltage law, KVL. So it's defined as around any complete path through an electric circuit, the sum of the increases in electric potential is equal to the sum of the decreases in electric potential. So I kind of say this a little bit differently. Your battery gives you a certain amount of voltage, and you drop that voltage across the loads in a circuit. The amount of voltage that gets dropped throughout that series has to be equal to the amount of voltage that you have in the battery. So what does this mean when we're looking at a series and a parallel circuit? Well, in a series circuit, we might have multiple loads connected in a series circuit. And so in that case, the sum of the voltage drops across each load has to equal the voltage of the series circuit, that is. So the battery, you could say. But when we have something connected in parallel, we have different loops, and each loop is a complete circuit. So the voltage in each loop has to be equal to the voltage of the battery that's the series or the parallel circuit's connected to. So when we have a series situation, it is the sum of the voltages, and we have a parallel situation. Each voltage on each branch is equal to the voltage of the battery. Now I say battery, but it could be any sort of source. So this is what you can copy down for Kirchhoff's voltage law on series and parallel circuits. And using this idea, we have a simple series circuit here. Our battery has 2.4 times 10 to the 2 volts, or 240 volts. We have 3 different loads. The voltage across the first load is 60. The third load is 60. The voltage across the first load is 80. So what's the voltage across that middle load, the V2? Well, let's pull up our calculator here, but it is a simple calculation. We have 240 volts. That is equal to V1 plus V2 plus V3. So to find out what V2 is, we subtract 240 by the V1, which is 80, and by the V3, which is 60. So we're left with 100 volts. So if I was going to write this down, I'll turn the camera on because it is just so we have this as well. You'd start with, for one, your VT equals V1 plus V2 plus V3, and VT is generally just what is the total voltage across or in a circuit. There we go, there's the camera back. We need to solve for V2, so that is equal to VT minus V1 minus V3. So V2 equals 240 minus 80, minus 60, which is, 100 volts. That's how we would write that down. Now I'd like you to copy down Kirchhoffs current law. So for this, let me just define what a junction point is. A junction point is where a circuit kind of breaks into another branch. And Kirchhoffs current law states that at any junction point in an electric circuit, the total electric current into the junction is equal to the total electric current out of the junction. In Kirchhoffs current law, we know that a series circuit has only one path. So there is really no junctions. So throughout that entire loop of that series circuit, the current through each load is equivalent to the current coming out of the source. So I in a series circuit is equal to I1 plus I2, or equals I1, which is equal to I2, which is equal to I3. But for a parallel circuit, we'll have a total amount of current coming out of the source. That current will then split into at each junction point, and the sum of the currents through each branch of the parallel circuit must be equal to the current of the source. So that's where we have our I total for a parallel circuit is equal to I1 plus I2 plus I3 and so on. So here is more to write down on Kirchhoffs current law for series and parallel circuits. And here's a question. It says calculate the electric current in I3, so branch 3 for this circuit. Well, let's turn the camera on and let's move this so we can see this a bit better. Just a bit more. So in this case, we have a one main junction point. We have a total current of 12.5 amps, and that is going to split. We have 2.5 amps and 4.0 amps. We need to find out what's left over. So our I total for this series circuit, for this parallel circuit, I1 plus I2 plus I3. And to find I3, it's equal to IT minus I1 minus I2. So it's 12.5 minus 2.5 minus 4.0, and that works out to 6.0 amps, or amperes. Amps is the short form or colloquial term we use for amperes. It's critical to understand the properties of circuits so that they operate as intended. Whether controlling a power plant or designing a circuit, we can use Kirchhoffs laws to analyze circuits to find unknown voltages and currents. And this looks like a really complicated circuit diagram. And we did talk about series and parallel circuits, but there are more complicated circuits as well. This is an example of a complex circuit, and in this case, you'll be asked to do an analysis of this by determining all of the unknown values. And I apologize that the picture is a bit unclear, but we will go through this and we'll solve for each. Let's start by first looking at the circuit and what we can solve. Let's move it a bit closer in. So this circuit here, what I can see is I have a V1, which is 6. My I1 is 4 at the top here. My I2 is known, but my I3 is not. My V2 is not known, but my V3 is. Can you see the V3? I don't think I can see it there. Let's push it this way. I can see it if I move it like that. So my V3 is known, my V2 is not. My I4 is not known, and my V4 is not known. So we'll start with Kirchhoff's voltage law, maybe, and see if we can find a complete circuit. So the circuit here, we have 18 volts to drop across each. And as we move around here, we drop 6. So 18 minus 6 is 12. Then we're going to kind of continue this circuit up to this point here. At this junction, we can make a choice and go this way, but we have an unknown voltage. Or we can go this way where we have a known voltage of 3. So going down to 3, we would drop another 3 volts. So now we have 9 volts remaining. Continuing along down here, we have our final load, and we have 9 volts remaining. So the voltage drop across V4 would be 9. Back to this little parallel portion of the circuit. So let's break this up and look at this as one simple circuit on its own, where this is our source voltage, and this is the load. Well, this is really a simple series circuit, and within this circuit, we have a voltage drop to give of 3 and a load here with an unknown voltage. This load has to be equal to 3. So this V2 is also equal to 3. And we can confirm that by following the path along. I have 18 volts. I drop 6. Now I have 12 remaining. Here I have to drop, well, I would have to drop 3 because I know I'm dropping 9 down here. So 18 minus 6 minus this 9 gives me the 3 that remains here. So that's our analysis of the full voltage situation. Now, how we would show this on our paper, you could write, we know V2 is 3.0 volts, and then the reason why we know that is because of Kirchhoff's voltage law. We know V4 is 9.0 volts because of Kirchhoffs voltage law. Let's look at our current. So the current through this branch here is 4, which means the current through our source is 4, which means our current through this branch here would be 4. So our I4 is 4 amps, and we know that we're at a junction here, and we know that at the junction the current going in has to match the current going out. So 4 goes in here, 4 is coming out, and we know that 3 amps are going down this branch. That means that what remains going down the other branch is 4 minus 3, which is 1 amp. So our I3 is 1.0 amps. That is known through KCL. And our I4 is 4.0 amps, known from KCL. So that's how we would kind of analyze that circuit. I know that was a little bit, might have been a little bit difficult to understand, so we are going to do this again. Let's move to another circuit here that is a bit more complex. So in this case, we have to find these unknown values again. Let's zoom in on the circuit. Let's see if we can get this whole thing in here. I don't think I can, but if I go a little bit smaller, so I don't have to move it around so much. So now we got it all in there, okay. So in this case, we need to solve for I1, V4, I4, V2, and looks like V5. So let's analyze this. We have a 72 voltage source. We don't know our total current coming out of the source, but this 72 voltage source means that we have to drop 72 volts across the circuit. So let's continue along here. On either of these paths, we don't know the V4 or the V5. So let's move on the path that has the V4 to start. I don't have a V2 here, so I can't go down this path if I'm trying to find out what my voltage drop is across V2 or V4. But if I follow the V4 along this path, I have 20 and 36. So let's turn on our camera here. And I can say that my V total equals V4 plus V3 plus V1. So my V4 equals V total minus V3 minus V1. So my V4 is equal to 72 minus V3, which is 20, minus V1, which is 36. And that would be 72, minus 72 minus 20 minus 36 is 16 volts. And I determined that using my voltage law, KVL. So that's one of my solutions here. Now let's look at that information. Since I have V2, I can now, since I have V4, I can now solve for V2. 72 minus 16, and then I have my V2 here, and minus 36. So that means that to solve for that, Vt equals V4 plus V2 plus V1, and V2 equals Vt minus V4 minus V1. So that would be 72 minus 16 minus my V1, which is 36. 72 minus 16 minus 36 gets me to 20. V2 is 20 volts, and that's KVL. Now let's take a quick break on the V2 because there's another way to solve it without having to do any calculations. And we're going to do that to solve for V5. If we notice here, this is a parallel connection. V2 is parallel to V3. And when we have a parallel voltage or potential difference, we know that those potential differences are equal on each branch. So we can directly just say that V2 equals 20 in this case. Same thing here, we have a parallel connection, so V4 equals V5. And since I know V4 already, I can state simply that V5 equals 16 volts because of KVL. Now let's analyze the current. Let's look at a branch here. We know that 5 amps kind of went through this branch, but we don't know how much amps went through that branch. We know that there is a 2 amps through this branch and 4 amps through this branch. So they would meet at this junction to be 6. So I1 is equal to I2 plus I3 because the 2 branches that go in to the junction that I1 is coming out of have to be equal. So we have 2 plus 4, I1 equals 6.0 amps. That is known through the KCL law. Now that we know that I1 is 6, we can follow that along and see that 6 goes through here, and 5 at this junction that 6 splits. 5 goes through this branch, 1 is going to go through that branch, and I just won't do that calculation. I'll just write down that I5, what was it, I5 or I4? I4 equals 1.0 amps, and that is known through KCL. So that's another analysis of a circuit using KVL and KCL. Let's move on here. What is wrong with the following information, and state whether you're applying KCL or KVL. The current going into a parallel circuit is listed as 0.5 amps, and the current coming out of the parallel circuit is 0.3 amps. Well, for a parallel circuit, the current out has to be the same as the current in, because that's how it's defined basically. The current going into a junction is equal to the current leaving the junction. Here's another misunderstanding here. It says, student measures the voltage across each of the 3 loads in a series circuit to be 10 volts. And he states the voltage across the source is measured to be 10 as well. Well, that can't be true because for a series circuit, the source gives us the amount of voltage that we can drop across each load. So in that case, if it was 10 volts at each of the loads, the source would have to be 30 volts. Or the student is measuring these loads incorrectly. For a circuit with 2 lamps connected in parallel, a student measures the voltage drop across one lamp to be 20 volts, and the student measures the voltage across the second lamp to be 10 volts. Well, if this is a parallel connected circuit, the voltage drop across each branch, each load in each branch would have to be the same. So it's either each branch is getting 20 volts or each branch is getting 10 volts. And last question. Students using an ammeter and notes that it reads 0.15 amps on the first lamp and 0.20 amps on the second lamp, and 0.25 amps on the third lamp. The student says the lamps are connected in series. Again, a series connection, when we're talking about current's the same in each loop. So that series connection has to have the same amps in each of the loads.